All right, thanks. So anyways, as I said, there's a lot of work generalizing this, particularly bond et al. 91. You can derive things like the conditional probability distributions for this happening under different environmental conditions, and that allows you to calculate things like correlation functions, clustering, resolve the sort of cloud-in-cloud problem, et cetera. So anyways, we are fairly familiar with this background. So how can this have anything to do with the ISM? Well, let's discuss some basic expectations in a turbulent medium. So the ISM is turbulent. Not many people are going to argue that. Now, in turbulence, let's make the simple assumption for now, although I could freely vary this if I wanted to. The velocity over the inertial range is going to take on something like a power law spectrum. So this, you'll just have some power law run where k here is the Fourier wave number, so the inverse scale that we care about. And this just tells you essentially what the velocity dispersion averaged on a given scale is. And that has some power law run. And if we know the velocity power spectrum, then at least in the simple inviscid unforced case, the Navier-Stokes equations tell you that there's a one-to-one mapping between the velocity statistics encapsulated in the power spectrum and the density statistics. And for the particularly simple case of isothermal gas, although that's not actually critical for what I'm going to describe, this leads to the very well-known result that the density distribution is log normal. And this has been seen in a huge range of numerical experiments. And essentially, so you've got a distribution of densities that's a Gaussian in the log of density, and it's got some variance S. And that variance is straightforwardly related to the variance in the velocity distribution. It just scales with the Mach number of the velocity distribution in a well-defined way. And if we average over a given spatial scale, there's a given variance on that scale. If you just plunk down spheres of a given size, you can say what's the variance in that size. And the way you calculate that is just by integrating over the power spectrum with some window function that just represents the sphere or whatever you're averaging in. And this is all pretty standard. This is basically just definitions. So we have a Gaussian random field in the ISM in the log of the density field, not the linear field like we do in cosmology, but nonetheless, it's a Gaussian random field. So if we want to count objects of interest, then we just need to define what defines a fluctuation or an object of interest. Well, it's things that are going to be self-gravitating. So how do we decide what's self-gravitating in the ISM? Well, you can write down the dispersion relation for some density perturbation or overdensity. And that's shown here, and it looks messy, but essentially what you're doing is saying that for a given perturbation, I've got support from angular momentum, this kappa term, the epicyclic frequency, and that dominates on large scales. I've got support from thermal pressure here. This is the sound speed, and that dominates on the smallest scales. I've got support from turbulence, and that dominates on intermediate scales, above what we call the sonic length, which is basically the spatial scale where the local Mach number is about unity, so below that thermal pressure dominates, all the way up to scales of order of disk scale height, where angular momentum dominates. And that's all competing against this term over here, which is gravity, which you see has the opposite sign. And if this whole term on the right-hand side is negative, then a perturbation's unstable. It's going to collapse under self-gravity. And the funny form here is just essentially an interpolation between the Jeans criterion on small scales and the Toomre criterion on large scales. There's nothing really new here. This is a well-known result. We can just rewrite this then and say that there's some critical density above which a given overdensity is going to collapse. And that's a much messier function than in Press-Schechter and cosmology. In Press-Schechter, this is 1.68, and that's really easy to deal with. This is messy, but it's still completely tractable. So what do we do? Well, again, just like in Press-Schechter, I want to show essentially what the method actually is for those of you who might not be quite as familiar. You can treat this in many ways, but in particular, you can treat this in a Monte Carlo fashion, and I'm just going to show one example of that right here. So what's plotted here is one Monte Carlo realization of the density field. I essentially pick a random point in space and use the power spectrum that I just get from the turbulent power spectrum to say, what's the density as a function of scale? If I start on that point and I plunk down spheres of progressively bigger and bigger size around that random point, what's the density I'm going to get as a function of that averaging size? And this is, again, just one random Monte Carlo realization of the density distribution, so one random point in space. And I can compare then the density on each scale to what would be required for that to be self-gravitating on that scale, for that region to be self-gravitating. And that's this red line. That's the barrier or the critical density at which you'd collapse. And again, on very large scales, this is dominated by the angular momentum of the disk resisting collapse. Then you've got sort of a minimum. Then you've got a long run where turbulence provides most of the support. And then at small scales, this shoots up as thermal and magnetic support becomes dominant. Now, in this particular case, you see that the density and this random point averaged on a given scale is interesting because it does cross this line. So it is self-gravitating on some scales. So on very large scales, we see that it first crosses at a scale of maybe 100 parsecs or so. So it's self-gravitating on 100 parsecs. So physically, this corresponds to something like a giant molecular cloud, which this is my incredibly poor cartoon of here. And that's going to collapse under self-gravity. But you'll notice that this doesn't just cross here and then stay above or fall back below. This has interesting structure. It crosses on multiple different scales. It's also self-gravitating on smaller scales. So, and unlike in the cosmological case, we know that gas in this medium can actually cool. So what does that mean? These smaller scales are independently self-gravitating. They can radiate, so they can collapse too. And their density is higher than the parent density, so they're going to collapse on a faster time scale. So we're actually accounting here for all the subregions in here that are going to collapse on their own. We're accounting for turbulent fragmentation. And this funny squiggle in comparison to this line is actually an analytic representation of this horribly messy process, turbulent fragmentation inside of some parent molecular cloud. So in this representation, there are two interesting scales. There's what I call first crossing, or what's generically called first crossing from the cosmological case. That's the largest scale on which you're self-gravitating, and you're going to collapse. And physically, that corresponds to things like giant molecular clouds in the ISM. But there's also, unlike in the cosmological case, a physically interesting last crossing scale. There's the smallest physical scale on which you're still self-gravitating, on which you're going to collapse, and on which there are no self-gravitating subscales. So this thing will collapse, but there's nothing inside of it that's also going to collapse, independent of the parent. So that's the smallest things that you're going to fragment into. This defines the mass spectrum of what you will fragment into. And if you look at the size scale and mass scales here, they correspond to things like protostellar cores, and to the extent that you believe that protostellar cores have anything to do with the stellar IMF, then the stellar IMF. Now, you can do lots of things to generalize this. For example, you can actually make this time-dependent, allowing the density fluctuations to obey essentially a stochastic differential equation. Again, it's messier than the cosmological case, but you can actually construct the analogy of a merger tree. This is not a halo merger tree. This is a GMC fragmentation tree that shows how, as it contracts, it fragments in time as density fluctuations grow. There are mergers occasionally between some of the subclumps. You said the smaller ones form first. The smaller ones collapse more quickly once they form. But some of these actually form successively as the parent cloud is collapsing. They weren't in the original cloud, or they weren't self-gravitating under the initial conditions. Yeah, good question, though. So we can calculate all sorts of interesting things here, and I just want to give you a couple-minute preview of some of the interesting applications of this, because really what I want to do is advertise this as a method that hasn't really been explored for calculating lots of interesting ISM properties that are interesting both if you care about ISM physics in its own right, but also if you care about it for the purposes of subgrid models and the like, because I think there's actually an enormous power here that whether or not you agree with the detailed assumptions I'm making, the method itself is very generalizable. So you can look at things like giant molecular cloud mass functions. If I use that first crossing distribution, calculate the mass function of those peaks, I get these black lines here. And the only difference here is I've normalized the model. You have to take the actual normalization, say the average density or surface density of the galaxy and its scale height as input parameters. They just scale out in the version of the model I showed here. But just taking observed values for these three galaxies, Milky Way, LMC, and M33, you get those black lines, and the orange points are what's observed. And there's no tunable parameter here that makes a significant difference. And you can ask, why does the shape emerge universal and in good agreement with what's observed? Well, To write down a full analytic expression for the mass function you get is horribly gory, and I will spare you that. But if you simplify to the range where turbulence dominates, which is this sort of power law regime, so above the sonic scale and below the disk scale height, you can show that the mass function simplifies to a Schechter function, not unlike what happens in cosmology. You've got an exponential cutoff at the global Jeans mass of the galaxy, which is up here, and you've got a power law run. And you can calculate that power law slope, but the important thing is that it's always close to -2 with some small logarithmic correction. Why -2? If everything that we put into our model were entirely scale-free, you would always get -2, because -2 means equal mass per log interval in mass. So scale-free processes will always drive you to -2. Now, the numbers we're putting in are not perfectly scale-free. If we recall this plot, say the barrier that we had to cross is definitely varying as a function of mass, so it's not perfectly scale-free, and this isn't just some power law, but it's varying very weakly. It's varying logarithmically over a wide range in scale. So you just get a very weak logarithmic correction. And for that reason, because this is a very weak logarithmic correction, it's really hard to push far away. Now, this is the mass function I get, making all sorts of different assumptions about the turbulent power spectrum, the Mach numbers, whether or not the density PDF is really log normal or has a power law tail. Again, scale-free processes drive you to this mass function. And the same logic applies for the mass function of cores. If you calculate the last crossing mass function that should be analogous to protostellar cores, this is what you get. This black line is the last crossing mass function. This red one is that first crossing GMC mass function. Of course, the number density and mass scale are very different, but the important thing is it has a peak at a mass that's actually, not unreasonable. And here I've just taken the Chabrier and Krupa IMFs and done the stupid thing of multiplying them by 3, because that's not a horrible approximation to the mass function observed of cores, but more appropriately, I should just compare directly the predicted core mass function to what's actually measured for cores in different regions. And that's shown here. So it's suggestive that we can at least get down to scales that are approaching the IMF scales. And of course, there's going to be physics between this and IMF that are very important that aren't in this model, like radiation effects, like accretion onto stars, like fragmentation into binaries. But we can get remarkably far with these very simple statistical approaches. And there's other interesting things you can model too. I'll just mention, you can look at the, say, size distribution of voids or holes. Just like we use Press-Schechter to calculate the void mass spectrum in cosmology, you can do the same in the ISM and compare that to holes observed in nearby galaxies in the H1 distribution, which there's a long-standing problem that these holes, it's always been assumed, were individually blown out by supernovae, and we don't actually see often the relics of massive star clusters in their centers, and this just simply argues you don't actually need that for many of these cases. You can calculate things like the line width size and the size-mass relation of bound objects. You can calculate clustering of giant molecular clouds and star clusters, just the clustering like you'd calculate in cosmology. Or you can calculate the clustering of cores, and that's what's shown here. This is just the correlation function that you predict for protostellar cores, again, with different assumptions about the turbulence that change the details, but not the qualitative result. You always get the result that I'll just point out is quite interesting, that if you note the absolute amplitudes of this clustering or correlation function here, they're enormous. So you always predict that star formation is very strongly clustered, very strongly correlated. And that's really just a very basic consequence of the fact that in any plausible turbulent system, most of the power in velocity fluctuations, hence in density fluctuations, is concentrated on large scales. So it's very unlikely that you'll get some totally local, isolated, small-scale density fluctuation that shoots you from the average density all the way up to a protostellar core. You're much more likely to form things like protostellar cores in embedded big objects that are overdense like giant molecular clouds. And that's not at all physically crazy or new to say, but this just gives you a way of putting it on a formal footing and actually making calculations from it. So I'll finish up. I'll just say again, as I mentioned, there's a huge range of ways you can in principle generalize these models to account for messier physics. But I leave that to hopefully people here who are interested in taking on some of these gory details. And I'll say, sorry, this was supposed to be cut, but I think it went a little crazy. I'll just conclude by saying there are certain things that this model tells you are fundamentally missing from itself on these scales. And those relate to old questions in star formation, namely things like what maintains the turbulence. I'm just assuming it's there. And of course, we all know that turbulence, especially supersonic turbulence, will dissipate on a crossing time. And very closely related to that, why doesn't everything collapse? The model itself predicts that if you allow it to evolve in time, eventually everything will become self-gravitating and run away and collapse. And it only takes a few dynamical times for you to do that. And so we recover the old problem that you can't stop star formation just from some top-down turbulent cascade. And so presumably something like feedback is needed to actually explain how this maintains its equilibrium over long time scales. All right, thanks.